I said now, Khyathat, last time we discussed, okay, these are D block elements, right? The middle, the middle part over here. So we just did the basic introduction, not just the basic. We actually did a lot of important things. These are your D block elements. These are not transition metals. And this was P block TK. We discussed that. P here, the last electron goes into a P in a P block element. Uh, group 3 is S2P1. Group 4 is S2P2. I mean, the outer shell electronic configuration. The last electron goes into a P. When you have a D block element, TK, for example, all of these are D block elements. So the last electron, but it becomes 4s2 and then 3d1, then 4s2 and 3d2. Here you have 4s2 and then 3d3, and so on up till 3d10. There are 10 elements, and the keeps filling up. There's d1 and d2, then d3, and so on. And there are two exceptions. Chromium and copper were two exceptions whose electronic configuration was slightly or very slightly different. Okay, instead of 3d4 4s2, it was actually 3d5 4s1. And instead of 3d9 4s2, it was actually 3d10 4s1. As anyways, we did all of that. Then I told you that D block elements are not all transition metals. I told you. Okay, a transition metal has the following properties. If those properties are not present, like high melting points, high boiling points, high densities, current compounds, and complexes and solutions, catalyst, variable oxidation states, if those properties are not present, so they're not transition metals. Transition metal, it's got to have these properties. Technically, a transition metal is an element that is going to form stable ions which have incomplete d subshell. So technically, that is what a transition metal is. And so iron 2 plus, if you write down the electronic configuration of iron 2 plus, it's iron, this is the stable ion, it's got an incomplete d subshell. Copper 2 plus, it also has an incomplete d subshell. Copper 1 plus, its d is completely full. So that means copper 1 plus is not going to behave as a transition metal. It doesn't really have colored compounds. Okay, and I'd also told you that this condition that the ion must have incomplete d subshell, it's got something to do with colored compounds, uh, which we'll discuss later on. But remember, transition metal, their ions are going to have incomplete d subshells. Okay, that's the definition of a transition metal. Okay, so who's not a transition metal? Zinc is not a transition metal because it's ion, it's stable ion, it's got a full subshell, d subshell, which is why it's not colored. Zinc compounds are white, and it doesn't exhibit any transition metal property as well. Scandium 3 plus as well. It doesn't even have a D subshell. I mean, it used to have a D subshell, but now it no longer has a D subshell. So that's also not a transition metal. So remember, any element whose ion has 2 electrons in the D, or 4 electrons, or 5 electrons, or 7 electrons, whose D is incompletely filled, that ion will behave, or the element will behave as a transition metal. As I briefly we discussed about why do they have high melting and boiling points. So I told you that when you move across the period, you have more protons. If you have more protons, there's more nuclear charge, there's more attraction for valence electrons. So I told you that the atomic radius decreases. So iron over here has a much smaller atomic radius. Calcium over there is almost twice as big. Calcium has 20 protons, iron has 26 protons. They kind of have the same number of shells. Calcium's electronic configuration is 3d0 4s2, and iron's electronic configuration is 3d6 4s2. So they have the same number of shells, but it's got more protons, which is why the electrons are more strongly attracted to the nucleus, which is why iron is smaller in size. So that was one thing. And the other thing was that they have more delocalized electrons. The other thing was Transition metal atoms also have more delocalized electrons. For calcium, it only loses the outer two electrons because the neighboring subshell is empty. So if you want to remove electrons, you have to go all the way inside the shell. That removing these electrons would be very hard. In iron's case, the 3D is full and there's very little energy gap between the two. These two subshells are like very close together. So if you can remove electrons from the 4s, if you apply more force, you can also remove electrons from the 3D as well. So more electrons can be lost. In case of calcium, only the outer electrons can be lost. So there's little energy gap between 4s and 3D. So you're going to have, so iron is able to lose more than two electrons, which is why if you look at the metallic bonding, calcium is going to be bigger in size, while iron is going to be smaller in size. Calcium can only have two valence electrons, while iron can lose a lot more than two electrons. So there's going to be more delocalized electrons in the metallic lattice of iron. So which is why the bonding is stronger. Smaller ionic radius, so they're more delocalized electrons. Hence, they're going to have stronger metallic. They'll be close to each other. They'll be more packed, and which is why they're going to have more density as well. Density is mass over volume. So if you can pack more iron atoms because they're smaller in size, so obviously they're going to have a bigger density as well. Plus, iron will also have a greater mass as well. So that's why they have more density. And then we talked about the variable oxidation state as well, which was I told you that since there's very little energy gap between the two subshells, 3D and 4, 3D6 and 4s2, you can remove electrons from the outside. If you apply a little bit more force, you can also remove electrons from the inside, which is why a lot of transition metals, they can have a lot of delocalized electrons and they can have variable oxidation states. They can lose the outer two electrons, but you can also remove electrons from the inside shell as well. Okay? तो ये सारा कल था, ठीक है? Now what we're going to do is we're going to talk about we're going to talk about catalyst later on. We'll start talking about colored compounds and complexes. Because that was the fourth point, which was, I mean, they form colored compounds and they form colored complexes. Now, when it comes to, I mean, before we talk about colored compounds as well, we need to understand what a complex is. Okay, and so we're going to talk about transition metal, complex. So I'm going to explain how a complex gets formed, and I'm going to pick the simplest complex that you're very familiar with. So starting with the first one, let's remember there's a bunch of equations and complexes that you have to remember. A lot of the stuff we're going to talk about now, there's an element of understanding, but you often have to remember them as well. So you know that if you have copper sulfate aqueous, what happens is that copper sulfate aqueous, it dissolves and dissociates and what it forms is Cu, 2 plus aqueous, plus SO4 minus 2. So you get dissociated ions. Now, this thing over here, this in fact is a complex ion. This is what it is. That it's a copper 2 plus ion that's floating in water. It gets surrounded by water from all sides, and it's completely floating in water. So, so copper 2 plus has 6 sides. I mean, it's got I mean, there's top, there's bottom, uh, there's a right side, there is a left side, and the dotted line indicates the z-axis. So there's one side that's going. Okay, there's one side that's going behind it. It's good. Take a second. And there's one side that's coming in front of it. So it's got, I mean, you can think of yourself in the middle, and there are six sides. Okay, uh, top, bottom, right side, left side. This is the back side. This is the front side. Now, this copper 2 plus aqueous is floating in water. What that means is that, so here's what your water molecule looks like. So you got a water molecule, which is a highly polar compound, and it's got two lone pairs, which are highly negative. It's got a partial positive H atom. Now, what's going to happen is the negative part of the water molecule is going to be strongly attracted to the positive part, positive ion. So copper ions are not just floating in water, they're actually forming a dative bond with water molecules. You get the lone pairs of water are very strongly attracted to the copper ions. And they're going to be attracted from all sides. So they're going to completely surround. So they're going to completely surround this copper ion. And they'll be sticking. They'll be sticking to this copper ion in the middle. एक दो और draw कर लेते हैं 1 second. So here's another. And then you have the last water molecule floating around and then coming in and then sticking to this copper ion. Okay, so the copper is completely surrounded by water molecules. And the water molecules are not just roaming around the copper ions. It's not just aqueous ions. They are forming strong dative bonds with this copper 2 plus ion that's in the middle. ये clear है सारों को? इस हालारों में से, is this clear? Asim, is this clear? Everything clear?
Yes, sir.
Yes.
So you'll be asked to draw this. Okay? So this is what a complex ion is. And it's the 2 plus charge is no longer going to be on the copper ion because it's going to get spread out. Okay? Remember when things combine, the charges all add up. I mean, you've got neutral molecules coming in, getting attracted to copper, which is 2 plus. So eventually what happens is that the charge distributes on the entire thing. So the whole thing is now going to be carrying a 2 plus charge. Okay, so the whole thing is now going to be +2. And the way this is going to be written is in short form, that's written as copper with 6 water molecules. And it's going to have a charge of +2. And this is known as hexa. Hexa means 6. Aqua, which means water. Copper 2 complex. Okay, that's what this is. So this is what a complex ion is. So let me write the definition of what a complex ion is. So it's an ion formed I mean, that's the literal definition. When a central metal cation creatively bonds to lone pairs of ligands. Okay, so what is a ligand? This thing that's bonding to it, that's called a ligand. I mean, the whole thing is called a complex ion. And this thing over here, that's known as a ligand. Okay, so the definition of a ligand is kind of the same. So what's a ligand? It's a species which has lone pairs. So it could be a molecule, it could be an ion, it could just be an atom. So species which has lone pairs and can natively bond. So and can natively bond with a central metal cation. So it's kind of the same definition. Okay, so is this clear what a ligand is and what a complex ion is? Clear है सारों को? Kasim clear Radha?
Yes.
Debate. Okay. And I'm going to give you examples. So there's lots of species that are ligands. You've got water. Normally this happens a, as a solvent, but you've got hydrated crystals as well. Ammonia is a good ligand. You've got OH ions, they are ligands. Uh, you have Cl minus one. You have Cn minus one. So lots of species that act as ligands. You could be given uh, any number of species which and you'd be asked to draw this complex sign. I said, but anyways, that's one of the complex signs. And this is CuH2O6. This is hexa aqua copper 2 complex, and you should know what the color of this complex is. So this is blue in color. Make sure you know this. And normally it's a blue solution. So this is what the blue solution is. Copper sulfate is blue when it's aqueous, because this thing called copper 2 plus aqueous, that's actually this thing. It's actually a complex, a copper surrounded by a water molecule. Now the next thing is that these ligands, they can you can exchange them. Okay, so I'm gonna do some ligand exchange reactions. So a lot of ligands can be exchanged. You can add another ligand, and the previous ligands can get substituted. So I would have to draw this again 1 second. So I'm just going to simplify this. Instead of drawing, I'm just going to write water over here. And remember, the oxygen should be drawn towards the copper because the lone pair belongs to oxygen. So this is and this is plus 2. That's just a ligand exchange. What is ligand exchange? Now, what happens is that if I add another ligand into the same solution, so for example, I add OH ions or I add NOH aqueous, then that solution is going to have, the solution is going to have another. So I'm adding NOH aqueous. Basically, what I'm doing is I'm introducing OH minus one ions. Slowly, what will happen is that these OH ions are going to go and they're going to start knocking away the water molecules. As the concentration of OH ions increases, the water molecules are going to get knocked out. Slowly, that's going to happen, but eventually, if you add enough NaOH, they're going to get knocked out. So, starting with, let's say, the OH ions come in and they knock out the water molecule. So, that's a ligand exchange that's happening. And if I add more NaOH, maybe another one of the water molecule gets knocked out. Okay. Actually, Yadak, is this part clear? Hala, Isaac, Ramesh, is this clear, brain clear?
Yes,
Yeah.
sir.
Achha, now
Yes,
in
sir.
the now in this case, what happens is this is like an exchange. You add another one, the previous one gets knocked out. Now in this specific case, what happens is that remember copper originally was what charge did it have? It had a charge of +2, right? So if two OH ions get attached to it, then what would be the overall charge? The overall charge would be zero, right? There's not going to be any overall charge. So what happens is that once you have a copper +2 and two OH ions get attached to it, now the whole thing over here, it doesn't really have a charge. The whole thing is now neutral, right? Which is why the water molecules that were previously attached to it, they would no longer be attached to it. There's no reason for them to be attracted to it. Okay, because they don't, the whole thing, the middle part doesn't really have a charge anymore. So they're going to leave. So they're going to eventually leave, and you'll just be left with copper and two OH ions. And that's going to form a solid crystal. Okay, so the water ligands that were sticking to the copper +2 would no longer be sticking to copper +2 once the OH ions are there, because the whole thing will now become neutral and there would be nothing attracting the water molecule. So CuOH2, pale blue precipitate is formed. Is this thing clear? You clear?
Yes, sir.
Okay, so CuOH2 is neutral. And what it does is it no longer attracts uh, the water ligands. And hence it basically becomes insoluble. It forms a crystal. So CuOH2 is formed. That's the next one. There are a lot of ligand exchange reactions. So we're going to do the next one, which is what if I add ammonia to it? You can remember copper sulfate. If you add ammonia to copper sulfate, let me show you. Okay, let me show you the. You've done this in the lab a lot of times, especially in the practical. You did these as cation tests. So let me just quickly. मुझे एक सेकंड देना जरा. अच्छा एक सेकंड. Let me just show you the actual. ये मैं शो करता हूँ कि copper sulfate blue solution, right? here, that's so the thing that you see on your screen, that's copper with water, right? Copper surrounded by water molecules. Now, what happens when you add NOH to it? So now you're adding the OH ion as a ligand. Now, the moment you add OH ions as the ligand, right? If you can see this on the screen, the copper ion is now surrounded by OH ions, but two of them. And it will become neutral and the water molecules will leave and it's going to start forming a crystal. And the same thing, if I add ammonia to it, so what happens in that case? In that case, what happens is that if I add, remember copper was surrounded by water molecules. The moment I start adding ammonia to it, the copper ions will now be attracted to the lone pairs of ammonia and they'll start forming another complex which will have ammonia in it. And that will be a slightly darker blue color. And the third one that you have to, or the fourth one that you have to do is copper, and you add HCl concentrated to it. And in that case, you get a green solution. The copper, which was surrounded by water molecules, is now surrounded by, it's now surrounded by Cl lines. Okay, so this is what you would see happening. Let me just go back. Okay, so going back to this. So we'll be doing all of that, okay, all the ligand exchange. So pale blue precipitate, that's important. You need to know pale blue precipitate. So what happens if I add ammonia to it? Achha, one thing about OH ions, you can only add two OH ions to it. The trouble is that after two OH ions, it becomes neutral. It stops attracting any more ligands because now it's neutral. So there's a limit to the amount of OH ions that are going to be substituted. Now, what happens if I add ammonia to it? So we add NH3 aqueous. And I'm going to pick this and I'm going to start substituting the water molecules with ammonia. Okay, so we had water and now the water is getting knocked out and ammonia is taking its place. Ammonia has lone pairs, so maybe this one gets knocked out. Achha, with ammonia, there's no specific number because the charge does not change because ammonia itself is neutral, right? So water is neutral and ammonia is neutral. So this ammonia is basically a neutral molecule is replacing another neutral molecule, which is why what happens is that copper was +2 and all the other molecules are neutral, so it remains +2, which means that it will continue to attract ligands. So there's no upper limit to it. Maybe all of the ligands they get substituted by ammonia. So this is Cu, NH3 4, H2O2, and the whole charge is going to be it's going to be +2. Or it could be Cu, NH3. NH3 could be N and water could be 6 minus N. Or maybe all of the NH3s or all of the water molecules get substituted at the end. Okay, but normally ammonia is aqueous, so there would be some water molecules that might still be sticking around or hanging around. So this is what your deep blue solution is. Okay, is this clear? ये clear है? Ibrahim clear है?
Yes,
Yes.
sir.
ठीक है. अच्छा, अब इससे आगे है कि there was one more left, right? The Cl1. Remember, this is deep blue solution. The last one that you have is the one when you add concentrated HCl to this. So HCl concentrated. So now there's going to be one major difference, and that is that it's concentrated HCl, so that means the ligand, all the ligands are going to get displaced. But what happens is that the shape of the complex, instead of the ligands bonded in an octahedral shape, they're now being bonded in a tetrahedral arrangement. So you have Cl minus 1 coming in. You have another Cl minus 1 coming in. You have another Cl minus 1 coming in, and another Cl minus 1 coming in. So remember, this was plus 2. You have minus 1, lone pairs coming in. Minus 1. This is minus 1. So the whole charge, the total charge on this thing is going to be minus 2. And so you don't write the individual charges because all the charges are going to get added up and they'll get mixed up. So the whole thing will have an overall charge instead of individual charges. And this would be known as UCl4. Minus 2. And its name would be tetrachloro copper 2 complex. And this one is actually, the color of this complex is actually yellow. But since the original complex was blue and there would be some of the blue solution still left, blue and yellow actually turn into green. So it appears yellowish green. Okay, and the name of this other one would be, I didn't name this. This one is tetraamine. There's two water molecules, diaqua and copper 2 complex. Okay, and I've written down the colors. This one is deep blue. Okay, so I'm gonna show. So there are 4 ligand exchange reactions that you see actually. The first one is copper with water, that's blue. Okay, let me write that. This is going to be your blue solution or blue crystals hydrated. Then they turn into COH2 if you add NOH to it. Then what happens is if you add ammonia to it, they get replaced by ammonia. If you add HCl to it, they turn into, they get Cl starts surrounding it. Achha, the important thing is about this shape. This is an octahedral complex. If you know what the shape is for 6 bonds, this is octahedral. Now, one of the reasons why this is octahedral is because water is a small molecule. It only has an MR of 18. It's like really small. So you can have more of them fit around the copper in the middle. You can remember the MR is 50. MR is just 18. So there could be one coming from the top, one coming from the side. But the trouble is, even the other ones, they're small. OH is 17, right? It's got an MR of 17. That's small as well. Ammonia is N is 14 and 3, that's 17. So that's small as well. So you can have 6 of them surrounding the copper in the middle. The trouble with Cl is 35. It's got an 35.5. It's got an MR of 35.5. So it's much bigger in size. When you're bigger in size, the trouble with that, it's got more shells. The trouble is that you run out of space. So you can't sort of fit so many Cls around it. So you can only fit 4 Cls around it. And with 4 dative bonds, that's just going to be a tetrahedral arrangement instead of an octahedral arrangement. Okay, so this one over here is a tetrahedral complex. Okay, so the rest were all, the smaller ones were all octahedral. Reason clear? समझ आइए? हालांकि, is that clear, Sark? Lumesa, Qasim, is this clear?
Yes, sir.
Sir.
ठीक है. अच्छा, the good thing is this is all you got to know. The other stuff is you have to know the exact same thing, but in the form of an equation. I'm just going to write, we're out of time, so I'm just going to write one equation. So whatever we did, we're just going to write the same thing in the form of an equation. So they're going to state that you got copper sulfate aqueous, and dilute NaOH aqueous was added. So what happened? Insoluble blue precipitate is formed, which is insoluble in excess. So what's going on? It's copper surrounded by 6 water molecules. So I'm going to write the equation. That's +2. You're adding OH ends to it. And it's, so the OH ions, they combine with the copper ions and they end up forming a pale blue solid precipitate. So this is aqueous. This was aqueous. And they ended up forming a solid precipitate. And the 6 OH ions, they got knocked out. 6 water molecules, they got knocked out. And that's what your pale blue precipitate is. Okay, so it's exactly the same. We did the diagram, now we're writing the same thing in the form of an equation. So we're going to complete the other equations tomorrow then, okay? So say कल continue करते हैं, ठीक है? I'll share the notes.
Thank you, sir. Allah.
चले, okay. हाफिज़.